So, sir, just started. So, hi everyone. Thanks for joining and welcome to the episode 11 of TechSagar webinar series. This series will be about the next generation computing, and it will strongly discover about the future of computing and how it is going to benefit the large businesses. As we all know that next generation computing has endless opportunities in very significant fields, and it has a strong opportunities to revolutionize the businesses when impacted. So for this particular webinar, we have our eminent speakers, Dr. Manan Suri, Professor at IIT Delhi, Dr. Alman Mukherjee, Senior Director at QPI. This session will be moderated by Mr. Vinayak Godse, CEO of TSCI. Thanks for joining.
Thank you, Humika, and thank you for all the effort setting up this webinar. And I welcome Dr. Mansoori and Dr. Alman Mukherjee as well for this engaging discussion on next-gen computing. So, welcome, Dr. Suri and Dr. Mukherjee.
Thank you, Dr. Vinayak. Thank you. Nice to connect with you, Dr. Amlan Mukherjee. Thank you for having me.
Yeah.
Thank you once again to have me on. I would like to correct my name. It is AMLAN, not ALMN.
I think that was
it's Amlan, AMLAN, Amlan Mukherjee. Thanks for having me here. Thank you.
Because I'm Amlan, because we work with QPI, Nagendra is very good friend on this. So for this particular discussion, we really want to start with Dr. Suri's. So the role of next gen. So every year, every era, like last so many 10, 15, 20 years of time, we always have gone to a situation where we talked about next generation computing every time, right? So now also when we talk about technology decade, and there are a lot of trends and ecosystem which is pushing us to think about what is going to happen in next generation from now, right? For this decade from now, what is going to happen? And one is the why we are talking about such a computing that will be required. Are those drivers and forces pushing us to think beyond what is happening in computing now?
Hello.
Yeah.
Am I audible?
Yeah, you are.
Yes, I lost your voice over the last two lines. Can you please just repeat?
My question was that the drivers that are pushing us to think beyond what is happening currently in computing, and why should we look at the new way of computing, new way of processing, basically. So what are the drivers that we see now that are forcing us to think about what the next gen computing requirement?
Yeah, I think that is a very fair question. So there are two things, right? One is that volume of digital data or digitization of data or information has just it's exponentially increasing, just the amount of information that is being collected. Other thing is that the ability to collect data has also become has expanded a lot. So the cost of generating data or collecting data has gone very low, with advances in semiconductors, or whether you call it sensors, or like any kind of platform. You take a cell phone, the amount of information that it collects, even when it is not used by the user, even when you are just carrying it around. So just ease of generation of data has gone up significantly.
Yeah.
And there are so many layers at which data is being generated that we are, like, without even doing anything meaningful, we are generating a lot of data. Everything, things getting connected is also generating data. So the cost to generate data, collect data has drastically, the ease of collection of data or generation of data has gone up. So when that happens, you end up with so much data that you start needing tools to analyze it efficiently, and that's when we start asking ourselves that, how to compute it efficiently or what to do. So I think that is the main reason, in my opinion.
And I think one is the endpoint which is made available to the end user, no matter how much end user is um, literate in terms of the digital, but very easy to use the kind of interfaces we build and kind of capability we brought into the endpoint, and made it easy for use of all of this technology, like from 200 megapixel camera to so many applications that you can use. So one is that certainly, another is, as you talk about, is now making system work is so easy and so easily accessible now in the current area of generative AI. We are talking about even simple plain English language can uh, create that prompt which can be responded by this generative AI. So that is definitely one important part in terms of why it is pushing, and then the IoT devices, everything becoming digital, all that is creating a lot of data, and that definitely pushes us to look at this one. So, Amlan, you are in the area of developing data center for such kind of high performance or high value processing of data, high volume, high velocity, high performance kind of data. So how do you see the, and this is like a very different way that you're approaching entire computational, including the quantum as well. So in terms of the user of this, so what you see, which is really creating that requirement of this technology that you are building?
Absolutely great. Thanks for this question. I want to exactly continue from the what Dr. Suri just said, right? This is exactly what is required right now. There's a lot of data being generated. However, converting from data to information, usable information, tangible insights, that comes only when you do computation over it.
Yeah.
And if I so one of the best examples that we have is this for example chat gpt. For it, all this data that we have in terms of what we have, humans have written, all the long articles on code on internet, that is what it is reading, right, and generating everything. So now the point is, if I look at from a point of view that what is next, and if I want to really get valuable information out of it, it requires really high computation power, really huge computation. How much in terms of power? I was reading this thing in this, even in fact for the large language model itself. So about if I scale it, what is going in, if we still go on scaling it in 2030 or so, with trillions of parameters or something that it will take like to train a model entire city of a city. So and even after that, entire planet. So it is eminent that it is going to be not possible if we don't have a breakthrough in terms of paradigms of computing. So herein comes, there are now, this is, I'm talking even classical computing, that there is this interesting landscape that we have. On the other hand, if I think about quantum, which gives us really another jump, what is known as quantum jump, a leap, in which we go into a paradigm in which where the classical cannot play. For example, if I want to simulate a molecule for drug discovery, I have a lot of data. I can do again machine learning that can help till some point. However, if I really want to really simulate the property of a molecule, it better be quantum. Now when quantum comes in, so this kind of problem cannot be handled by any classical computing of any magnitude. This would be very difficult. So there we need quantum. So what I wanted to ultimately impress upon is that if you go about classical or quantum, you need right now really this different paradigm of computing, a different way of computing, just not this pushing, going ahead. And another point with that is that it requires together, it's a co-development, not only of software, but the co-development of hardware. We require new hardware for both the data centers and large language models or machine learning, what is coming in the future, and even for quantum. So we really require new quantum or even classical computing platforms in terms of hardware too.
Yeah,
That would,
and we will certainly, I think, discuss about quantum in some time, but with Professor Suri here, I certainly want to understand in terms of semiconductor hardware ecosystem, in a classical computing ecosystem, what are those things which are happening? Uh, as a end user, we definitely know that the processor is increasingly, our mobile phone has now 3 nanometers processor basically. So one is the processor, but there are many other areas and nuances. I think if you can dissect that in terms of classical computing model, what is really happening and where we are reaching, and that inflection point where probably non-classical quantum computing will come to that after a while. But we just let's spend some time on the classical computing paradigm and then see the next paradigm, and then we'll see how the transition will happen between taking both of these together. So, with Professor, we want to hear from you on in terms of all these technologies, semiconductor and other hardware ecosystem, how things are evolving to keep up the space with this computing requirement.
Sure. So on the classical side, as you mentioned, yeah, definitely there is the separation between classical and non-classical. But at least on the classical side, has been the mainstream of industry and all implementations of computation ever since commercial computation has come into existence. So last 5-6 decades, classical digital computing, or what you call as von Neumann computing, that has been the mainstay. More than 95-98%, almost all computing that we touch upon in our lives is digital, classical digital von Neumann computing, and it's going to be that way for a lot of things in the time to come. And interestingly, how it has moved ahead on a very systematic roadmap. All these years, all these decades, it has progressed on a very systematic roadmap, very rule-based roadmap. There are some metrics, performance metrics, which the researchers or industry try to optimize or improve year after year, whether it is the power, energy, or the area, or even the latency or the operating frequencies. So that has dominantly been driven till date or till recent times by scaling, or Moore's law in the semiconductor industry and transistors. There is a continuous quest to make transistors smaller, make nano devices, nano electronic devices, make devices smaller with each generation, with each technology node, and then apply some tricks at the different layers, at architecture layer, or at circuit layer, or even going above the stack at the algorithmic level. So that has all fit quite well into place, and generation after generation, starting from the 4004 to Pentiums, and then to Xeons, to what we are seeing. Everything has progressed pretty systematically. Now, since last few years, it's where we are. There is always this question keeps coming up in the semiconductor industry, that there is a bottleneck where you face a physics-based bottleneck, whether it is the lithography or whether it is the behavior of some material. So every now and then, engineers or researchers are posed with this question that we are at a dead end of physics, and then there are talks like now silicon will end, or something new will, something drastically different is needed. But somehow or the other, you throw companies or governments throw 3-4 trucks of money and 100 engineers in a building, and it is solved, or some shortcut is found for the classical computing to survive a few more years. So while staying within the, so traditionally scaling, in short, your answer to your question was scaling has kept the traditional computing alive. And then on the architectural side, it's more of parallelism or better management of the data flow, and then from microcontrollers to microprocessors, and then going towards more custom or specific architectures that also enable your current applications like AI, deep learning, and all, whether it is GPUs or accelerators or edge accelerators. those things are being explored, and a lot of activities happening in that direction, custom architectures, while still staying with conventional devices, conventional nanoelectronic devices, not very radical. Let's call it ultra scale devices, not radically different in operation, not yet beyond silicon, but still in silicon at advanced nodes. These things are being tried. So so that is the point till now. But going ahead, the scope for some real different physics, some real non-silicon based devices, the doors are also opening up. Some real non von Neumann computing approaches is also opening up. Analog computing keeps coming every once in a while, in few years, with some promise, and as technology or capacity to fabricate technology, semiconductor technology improves, there are some niche realization there where we have new type of architectures. So if you say traditionally it has been scaling and some architectural level parallelism, and then going ahead it will be more exploration of more materials, more new type of materials, or more new type of physics based effects to advance in the next era of computing.
So this entire game that we see in terms of one speed and other is the power, right? So a significant part of that is to till now, although there's a physics limitations as well in terms of, and that's why we're going for the other material. But before we go to the material science for computing, so I think machineries that you use to manufacture plays very important role, right? So in fact, in the entire supply chain ecosystem, what we see currently, the US government is focusing its attention to the access to such machinery which help you to manufacture such kind of a high end processor system. Basically, can you just throw a little bit light on the manufacturing capability, which is taking us to the limitation of physics, basically?
Yeah, certainly. See, it's also more than machinery. It's like the entire process flow.
Yeah.
State of the art CMOS process flow. If we talk about it, will be not just one piece of equipment, but an entire clean room going through more than upwards of 1,000 steps. And so it's definitely the machinery, extremely high precision clean room equipment that is needed. Then it is also the control and over the yield, or the what is the kind of output, the extremely tight control on the variability, or how the things are, quality control, extremely tight quality control or behavior control of that is the other challenging requirement. And then there are also some supply chain related constraints, like some specialized materials or specialized devices, or technology access. So all these three things together make it complex. But then again, it's not impossible, because many countries are doing it, right? So if with some planning and some investment, I think it is possible, and it should be done to have that capacity domestically also.
So
Maybe I would like to add here something. Yeah, so for example, but it seemed a bit easy, but I am going to give the hard part. Let's say take an example, the 7 nanometer TSMC process. So again, machinery and all this thing. The machine that actually makes it, it comes from Netherlands.
yeah,
It is a company which is ASML which makes it.
yeah, yeah.
The
I was
heart the heart of the machine is a 13.5 nanometer extreme ultraviolet light, which is generated by a laser, which is doing essentially plasma emission by bombarding on I exactly forgot, probably some argon ions or something. So then this light is then precisely controlled and made to on a put on this wafer, and this wafer has a very precisely controlled nanostepper. And then the optics, only one company makes the optics for this ASML. This is Carl Zeiss from Germany. So you see, this is really constrained and really high tech. Meaning, what I'm talking about, this machine is not even 100 million; it's way above that, if the cost of such thing. and very high precision stuff is there. So the way we are going towards it, and already I'm claiming 13.5 nanometer, which is the wavelength of light, is making 7. So one can imagine it's like some tricks to do beyond this diffraction limit, right? So yeah, so there is a lot of challenges that is involved. It seems to be easy
Yeah,
that we do a lot of this thing.
and
Please.
access to kind of machines becoming a big challenge, and some restrictions are being.
Yes, of course.
Ability to access this technology in building is not that easy as it used to be basically. So that's definitely one important part. But now coming to different form factor, both question to both of you, right? So form factor in terms of IoT and something which goes into networking, something which goes form pattern use of, right, goes into data center. So how do you see the computing is evolved for different use and different form factors? So any of you can start and other can add to that.
Okay, then I start. Okay, yeah. So what I see right now is this, that usually when we say form factor, you would see, how big is the chip, right? When you ask, I'm wondering like that. So yes, there is I would see there is kind of bifurcation there. There'll be a monolith, usually monolith design of large chips. We will let's say going into GPUs, which will be larger and larger, but there is an increasing trend of multi-nodal integration, which is going to be absolutely important. So what I'm trying to say is that you have something in 22 nanometer node, something in 7, something in 3, something even maybe higher, 65. All will be integrated, and then multiple things will come out. For IoT, it will be different, and then for computing, something based on RISC-V, something on some other node is there, and then there will be even lower, simpler, cheaper nodes in which we'll have very small passive also devices, kind of very low power devices. So there will be a large spectrum. So on the one hand, there will be monolith, large chips, reticle of entire wafer, trillion transistor going up for, really, brute force computing kind of thing for GPUs and models. And then there is another part where there's a mixture of complicated things coming up. So this is what I look at when you think about form factors.
Yeah, sorry.
Yeah, so form factor again, like form factor is at two levels. You can look at it. There is the obviously the form factor of the chip, and then the form factor of the complete system itself. You know that whether we talk about desktop form factor or a rack mountable form factor or a tower form factor. So that changes because of many other aspects or many other peripheral aspects also. If you that has stayed pretty much in some standard blocks, like the size of the desktop cabinets has stayed like that, the size of the rack mount servers has stayed like that, but the computational power that goes inside the same size of cabinet or rack, that has been increasing. So from the user side, those form factors more or less they get standardized, but what you get inside uh, per square centimeter or that drastically that has exponentially increased. So more drastic change in the form factor has really happened at the chip level, and now we are also looking at technologies which are 3D or 3D integration or 3D packaging, so that will go even much higher, like phenomenally higher, because chips will be made in the or are being made in the third dimension also. Computation and storage both are being put in the third dimension also. So that is leading to a lot of significant changes in the form factor, but to the user that is many times it's not visible in the final equipment. So in term it's visible only functionally in terms of performance. So
So let me ask this. We are with you, Professor Suri. So some people
sir, your
can.
voice is breaking. If you can just maybe increase the sound or
Yeah, is it okay now?
Yeah, it's better. It's better also.
Yeah. So let me, if you are with you, so let me ask you the question about so the devices, especially the mobile, right, and which probably revolutionize the way the computing would happen, and end user get immense benefit out of it basically, and we see that coming as a key differentiator in terms of pushing the boundaries for the semiconductor technology, right? So every company is now in the race of either I was just looking at the Samsung, which is talking about 500 Mbps per Mbps camera coming in phone, 1.4 nanometer processor coming in the phone. So help us understand how that push has really helped and push the boundaries of computing.
So your question is about some particular device, or
My
I
question
could
is
not get
mobility, how mobility and the mobility push the boundaries of computing actually.
mobility in terms of the transfer
Phone,
of.
Apple phone, Google phone. So they expanded a lot with respect to the hardware available in mobile.
Yeah, yeah, yeah. So again, it goes back to our first point that what is the need, and because it's not just mobility but also the ease of use. All
Yeah,
these there is so much emphasis on user experience, and when user experience improves, the technology just becomes so accessible to such a wide audience. Everyone, not just people who are trained in technology, but to everyday users. So that is one thing. Plus, then the on the mobility part, as the bandwidths are also increasing, now we are going towards full 5G, and then possibly later also to 60. Then that also eases out how much information or what quality of information you can easily transfer. You can shuttle or move to different places. So that all adds up. It all adds up. It's a positive feedback. That. Many times we see that uh, high-end computing systems are being used to design the next high-end computing systems,
yeah,
and then you ask yourself that okay, that how many of the common users will use this for day-to-day application, but it is driving that. So it's a cyclic thing. So technology itself, the capacity of technology itself will lead the road for even more advanced technology to come after, or sometimes it would create the need for that. If let's
yeah,
talk about data, for instance. If the such high bandwidths were not there, or if video transmission was jari, people would not think about doing edge vision processing or edge vision analytics. If in the first place you could not stream that much of visual data in a real time, it
yeah,
would be meaningless to do any analytics on it if it is not being transmitted in a real time. So as different verticals of technology, whether it is transmission or bandwidth, or as they, or even storage, so much data, so much computing or analytics today we are talking about based on the amount of stored data. So storage technology or memory technology has progressed a lot. If it would have not progressed so much, then you could not hold so much data in one place. If you cannot have that much data sitting in one place, you cannot process it or derive any meaningful big data
yeah.
analytics. So it's one vertic. All these verticals, they feed back to the each other's need and requirements.
So Amlan, the same question to you. So how this competition between this player and bringing the best thing possible to the market, and especially the end user market, basically really push the boundaries of uh, semiconductor industry.
Okay, now that this question is a business question, right? So
Yeah,
it is about that's pretty clear that when you have capitalism, so capital is when in capital is deployed, it is deployed for to fight the competition or making better, as they say, better, faster, cheaper products. So it is like a good competition for the customers. So I would say the question is how customers are driving it, in a sense that we had pagers one time. There was a long old times we have pagers, which was like a small mobile device and you could text only. So then came mobile phones, nobody used pagers. So exactly this thing, the customers are driving the process forward. It is not how the competition is there. I would say it's rather the customers who are driving it. Same case for mobile phones too. Customers are demanding that we want to play games on the mobile phone. Therefore, the computation power of mobile phones are going higher. Customers will demand AI in mobile phone. Therefore, mobile phone will change and do.
Sometimes
Customers are
I
demanding.
think
Yeah,
maybe sometimes we have not asked for this thing, right? Because they are pushing, and that's why they are telling us ki probably you can use it for this purpose as well. Sometimes it's also innovation pushing us to use it more, right?
true. That is true. Particularly, for example, for iPhone or
Yeah.
rather this iPod,
Mm.
there was there, but this kind of when you build something very good, this suddenly market is created rather than this thing.
Yeah.
However, I always wanted to point out this that once market is created, it is true that we can push it somewhat, but that
Yeah.
feedback should happen very quickly. Otherwise, so still I would stand my point that it is the customer driven where the business or this progress of high end computing is always going. Yeah, thank you. Yeah,
So let me come to some of the area. Uh, uh, so you are in data center technology, right? And if I categorize it well, right?
yeah,
But and there is a definitely a premise of data is pushing to cloud, and you need quite a good capability there. But now against that, there is edge computing is also emerging as a way to manage the workload going for processing basically. Does this uh, changing the way the technologies are evolving in this? How much edge
yes.
computing?
Yeah. So first of all, it seemed like it was looked like two competition. You're saying cloud and edge. So
Yeah.
I would like to put it like no, no, no. This is not a competition. This is actually a collaboration. If you think about it,
Mm.
not everything is can be done in the cloud. Not everything can be done in the edge.
Mm.
So sometime let's say if you have a small device like for example even with the GPU like Jetson Nano, this is a small device but it cannot run, you cannot train models on that, but you can run small AI models on it. So if you have sensors integrated to it and then quickly do some AI on it and filter out the important parameters out and feed it to the data center, and data center is doing the training and maintenance and the big strong computation or hard computing task, then this is a win-win situation.
Mm.
So
Mm.
this is how the things will evolve more. So and again from hardware perspective, these are completely, as I said before, as also Professor Suri said, right, that there will be 2.5 3D integration packaging. So the edge computing part would be like that. And while if we come to the cloud, it will be more like monolith, reticle, big computing power sitting, even quantum computing crunching on numbers. So you see the synergy between both of these kind of areas that will happen both in hardware aspect and in software also, essentially driving all this. Yeah.
So some of the area, Professor Suri, one is the the entire need of deep learning and machine learning, the pushing the way the semiconductor industry. I was sitting with one of the startup in Bangalore base, and they were talking about how they are trying to find a semiconductor solutions to help you process millions of node data at one chip, basically, right? Chiplets and many other technologies. So, can you help us understanding how semiconductor industry is responding to the tremendous amount of the processing required in one chip?
Yeah, so the as you might also be aware of all the AI winters and how in the field of AI many times there is a lot of traction and then things go down, fizzle out. So in fact, I believe, in my opinion, whatever advances or whatever excitement that we are seeing related to AI or deep learning these days or in the recent 2 3 years, um, it is actually happening because of the advances in semiconductors. The math that you see in the field of AI deep learning, fundamentally that math has been around for a long time, and it's not that some breakthroughs have happened at the mathematical level, fundamental mathematical level. It's uh, doing a lot of that math one after the other in a sequential way. That has what has become very easy by the advances in semiconductors with specialized chips like GPUs or high-end processors or accelerators. That has when you're able to do those million mathematical operations on your desk, that is when it becomes meaningful AI. If 20 years ago, if those operations took 5 days, then we would have not called it AI. We would have, or it would have just lost its value. So it is actually the new chips, the new kind of storage or the advances in the semiconductor chips, whether it is your processors or specific architecture that has actually enabled it. And now this it's working both ways now that new designs are coming, new chip designs are coming, which are very specific to certain algorithms, certain class of algorithms, ASICs, and also the exploration is happening in both digital as well as analog realm. So the semiconductor design or computing hardware industry is responding with a very high speed, with a very strong turnaround time, very short turnaround time to the advances in AI. And in fact, I would go to the extent of saying that since few decades at least, while there was very strong scaling happening in the semiconductor industry, in the core system architecture or core computational architectural or firmware level software, there was not much innovation happening. All the gains that the user experienced was actually coming only because of steady scaling in the at the hardware computing hardware level, year after year, and the AI revolution also has actually come about because of the GPUs, which is a pure hardware manifestation, a pure hardware realization even before the algorithms.
So Amlan, you want to add to this quickly?
Yes, great. I think this is absolute. I could completely second what Professor Suri just said. There is exactly this scaling that hardware, which people don't realize probably. AI was introduced long back, really, really long back. There was AI winter only in 2010 onwards when GPUs become ubiquitous. It became like caught the fire, and now we have Chat GPT, right? Uh, exactly. And but I want to also point out that yeah, not only that, the semiconductor industry is really pushing it forward in a sense that even newer, beyond CMOS and I would say even photonics. For example, photonics computing, which again I work in, uh, this is also becoming a kind of mainstream. Two companies are offering again such GPU-like capabilities at a low power. So one of the thing that is, the semiconductor industry is working on is making things low power because this more we compute, more we consume power. So this is where we also are looking at. This is a threshold perhaps we will hit more sooner than even the node and quantum effects coming in and making transistors not work. Even before that, this power aspect will limit a lot of computing and therefore, but the demand is high. So one will semiconductor will push in a different way, even beyond even electronics into photonics. That is what I wanted to say.
Yeah, I think we will certainly come in short while on a quantum as well. But before that, I just want to uh, discuss on one part is the different IPs and standards which are evolving. I was just trying to take a um, view on PCI Gen 6 standards, right? So it's a data connector standards and how they will be evolving. And by 2027, Gen 7 will come and it will talk about 512 Gbps per second, right? And the standards are helping you to, and that's why it is making it more interoperable and then also usable for the different kind of workload. So my question is how these standards are really evolving to design it better and work with entire ecosystem better. That's one question. Another question is um, mm, uh, how the IPs, different IPs, the designers are creating. So, for example, we're using the GPSCI Gen 6 standard and the data connector. So, I've seen 3-4 companies in India which have developed IP, and those IPs are now going into set-top box, which is delivering 8K videos basically, right? So this entire supply chain of a ecosystem. So there are two questions here basically. One is standards, the other is the different IPs basically they are coming together to develop overall system. I can start with Professor and then come to Amlan.
Yeah, so standards is a very, I would say it's a very tricky thing. Depends whom you're talking to. At different stages of a technology, standards help some people, and in some cases they inhibit. So, so the positive side of it is that if something goes into a standard, and if it is a consortium or if there is a wide participation in that standard, then people doing different innovation with their IPs, if it conforms with that standard, then the IP becomes compatible with a lot of other peripheral things or a lot of other peripheral products, provided it is a wide enough standard, provided it is not a very limiting standard. So, in my opinion, standards should be given importance only if they are wide, they are broad based, they are not limiting to a few industrial players, not monopolistic, and yeah, that is one point. The Yeah, so it should not be a restrictive standard, and so that was the first part of your question, right? How standards, and can you please repeat the second part again?
My second question is the different IPs coming together, right? This entire supply chain is different people building different IPs and coming together and creating one set-top box for that matter, one mobile for that matter. So how these IPs come together, and what are different IPs which you see in your day-to-day interactions, which will probably become critical IPs and be part of the overall system, basically.
So on the IP side, mostly the tradition was that different IPs would come together at either at the software level or at the PCB level, at the board level. But off late, with some new manufacturing techniques or new manufacturing interesting developments like chiplets or TSVs or interposers, it has even opened the door for IPs, different distinct IPs coming together at the chip level or at the die level or at the silicon level, which was not a very easy possibility before. So before it was just like two softwares or two soft IPs sitting together in some system, but now so on the IP side, at the pure hardware or process level IP also, it is becoming more relevant. But then, we one thing that needs to be seen in the hardware industry also is that the open source movement, because both these, whether it is IPs, whether it is standards or IPs coming together, just like in many places, the software or the AI segment has also been extremely successful because of its open source approach. So that is something which has been very slow or very deficient in the hardware ecosystem. So maybe in future that would also increase, and that will, so that is something which I think maybe the market or the industry would lead at some point.
Is it because the players are still limited in hardware industry? That's why it's happening, or why? Yeah.
It's a little bit because of the genesis, how things evolved. Like fabs were with limited equipment, of fabs were with limited people, so process recipes came up limited, and even the semiconductor CAD industry was only with a handful. The design CAD industry still continues to. So there was a lot of consolidation, or semiconductor industry frequent consolidation, both at the design side as well as at the fabrication side. But now there are some initiatives on open source are starting. So I think it's more of economic and historical reason why it is in this way.
Amlan, you like to add from your side on these 2 points?
Yes, exactly. I totally again once again with agree with Professor Surya. I'm just going to add something, maybe an example, few examples. Say, I am not a great fan. I should not say it here, but not great fan of IP being so very hard IPs being put, and things which I would say it is detrimental to development. I have a example, counter example. In fact, if you go to Shenzhen, China, these people when they make those even earlier from now the drones, first drones that become ubiquitous again another in the entire planet, they made it. In a sense, they were just fiddling around with lot of even we should be like essentially copyright violation, I would say. But this is rampant. But what has helped is rapid prototyping and development of the hardware. So if we see from India's point of view that if you want to march ahead faster and faster, or emerging tech, so IPs I would rather say is kind of, it can sometime rather being an enabler, can also a constraint. A good example once again is the EDA tools. There are essentially duopoly, right? You
Only two
either
players
go,
in India. Yeah.
yeah. So then otherwise the foundries will not tape out your chip. So that kind of thing, I think, there in open source, if it is somehow worked out, a lot of things would change. Again, coming back to the now to the standards, looking from the IP point of view, standards I believe is set ultimately by the again by the market, in a sense that what is being sold, what is being used, and what is being really then when it matures enough. Before that, if you try to enforce something, it is going to be much more of a futile exercise, and ultimately it will be going somewhere like that there. So I would again come go with Professor Suri saying that sometimes it's a necessary evil, but yeah, rather be in a way should be managed well, should not be putting down innovations rather than forcing something on top of it. Yeah, that would be my
So let me now come next level of questioning. So I'll certainly come to quantum, but I would certainly like to discuss with Professor Surya in terms of the different material being now thought for computing, right? So um, and for very different use cases, basically, right? So help us understanding the role that other materials than silicon will play in the computing that we'll see from now.
Sure. So I cannot speak for all materials, but at least some areas, some work that we do is, so we work on a lot of storage or semiconductor memory technologies, and there different type of materials are used, which are all silicon compatible. They go with the mainstream silicon CMOS process flow, and different type of materials. These can be magnetic materials, magneto-resistive materials, resistive materials. What is happening is that conventionally the memory or even memristive materials, which are more commonly known as memristive in popular literature. So traditionally, the materials that were being used for computing, or the devices that were being used for computing, were purely logic based devices and digital gates. And now in new forms of computation, when we are looking at some mixed signal or analog or hybrid computation, which is not like conventional von Neumann computing, or even bio-inspired computing, or neuromorphic computing,
Yeah,
or
yeah.
even memory-driven computing, there these new interesting materials or these new interesting devices bring a lot of possibilities. And one of the reason for that is that they have a different physical mecanism to work, different physics, and that sometimes their behavior, their response to currents and voltages, that leads to some energy efficient computation. For example, if you were to do addition or multiplication using all transistors, you would need a lot of transistors in silicon. It would consume a certain energy, it would consume a certain area. If you were to go some novel memristive devices, which are fabricated on top of silicon or along with silicon transistors, you can do that in a much energy efficient way with much fewer devices or much lower area. So, uh, so, so uh, making the, what I think Dr. Mukherjee also mentioned before, low power, the need for low power. See, when you compute so much, on one hand you have got so much computation capability and so much computation requirement, but if it is not energy efficient, then you will do more harm than good. So each computing action needs to become more and more, as we are increasing the computation speed. It's important that the energy footprint of each computation action goes down. So that is where these new materials are bringing a possibility. That is where they are opening the doors.
So, Dr. Amlan, let me come to you on now the work that you do, right? And quantum now, until now, we largely talked about bit, but now qubit is taking over, and now it's real, right? So now some of this 127 qubit computer is available for us to use and process data, right? So how that will change the paradigm of computing?
Hmm. Yeah, that is very important. So what I wanted to say here is, look, till now we are talking about classical. So there are problems which classical computing can never, handle, or rather cannot handle efficiently. One of the example I already gave is, let's say you want to do a, let's say, a antibiotic discovery or invention, rather, not discovery. Till now, antibiotics, the way they were discovered, is that the biologist will go into the wild and pick out the exact, really do detailed study in lab and try to pick out the antibiotic molecule that is nature produces, and go on clinical trials to do that. On the other hand, we know the ribosome structure of human and ribosome structure of bacteria. They're very similar, but little bit different. Exactly the molecule that will fit in the bacterial ribosome, but not fit in the human ribosome, is what is the structure of an antibiotic. So now that if I give a quantum computer this question, that okay, given that we have oxygen, hydrogen, carbon, nitrogen, can you give me the antibiotic which will attack this ribosome structure? So this kind of question can never be asked in a classical way, because the molecule itself is a quantum mechanical object. To simulate that, it will be next to impossible. However, when you have a really powerful quantum computer, this would be possible. So one day we will be able to do drug discovery with this. Similar is the case. Another example I usually give is something like, called Grover's search, an algorithm given by an Indian, Love Kumar Grover. Uh, this is the best search algorithm known to human being uh, on an unstructured data set. So an example would be needle in a haystack. A needle in a haystack, if you try to do classical search, you will take a looking glass and look for each of the hay and try to get what is the needle. But if I put the entire thing in water, what happens is water will act parallelly together on all the hay, all the straw. It will just make it float, while the needle will just drop down. So this is like parallel computing through nature. So this algorithm essentially kind of does this, that you can search the entire phone book in one go, and the phone number, even if it is not indexed, that phone number just comes floating away out. It just filters away in one, in this process of doing that. So herein I would like to cite two three powerful things that is not possible classically. That's why it is happening. It's called superposition. There is something called quantum superposition, for quantum entanglement, and then quantum interference. All these things come together when it is in proper done properly. This kind of really different paradigm of computation can be exploited to get very interesting results. Again, all of this again stands on the giant of the shoulders, that they want hardware to be proven, stable, and really standardized. So that will take some time, but we are on this right path.
So currently, I think 127 qubit is easily available. So is 400 qubit is coming, right? So where exactly is going in coming 2 3 years of time is how much qubit is available and what kind of processing they will add.
Yes. Now I would give you a very interesting insight. Probably this is what will happen is this progress of number of qubits will stall, and not because the qubits are not scalable. It is interesting that the qubits are scalable, but the cooling system, the thing that cools the qubit down, that part is become extremely expensive. So I was in Finland, in fact, in the factory of Blue Force, which make these cooling devices, which are called dilution refrigerators. So they showed me a big room, which is a cooling system, which you can walk in and sit down inside, which is the fridge. It cost $4 million before the market is still in development. So that will be required to have 1,000 qubits. So you see, so now what is the next one? If I want to do 4,000 qubits, sorry. So therefore, there is the light. So there is the, then I would see that this kind of development in a very soon, probably we will be able to hit 1,000 qubits, but beyond 1,000 qubits in superconducting systems. Now it is becoming system specific. Superconducting qubits is really hard to realize given the constraint of heating. However, there is a loophole. Again, semiconductor comes to rescue. If you have a control chip which essentially reduces the number of control lines from the top to bottom, then more than 4,000, even millions probably is possible. Again, the next constraint would be size of the qubits. So one would hope that
Then the
exponential growth will come out.
the multiple thousand people can be together. So how that limitation will get over? So how the semiconductor will play a role in terms of scaling?
Yeah,
So I'll just explain that
exactly.
later.
So that is very interesting actually. This is the bottleneck of quantum computing, what people were not talking about. So
Yeah,
what is happening right now is this: there is this fridge, which is a dilution refrigerator, which has, let's say, the base temperature is about 10 millikelvin. So what
yeah,
is 10 millikelvin? If I stand at 10 millikelvin and look at room temperature, which is like from the from my height to the roof, this is will be the temperature difference in that fridge. That would be like I'm looking at the surface of sun. So
hmm,
imagine the surface of sun is just a meter away from me, and
yeah,
that is the level of heat difference in that, and that is
yeah,
what is being created by this fridge.
yeah,
Now, the way quantum computer is or qubits are being accessed is that you have microwave lines
yeah,
from the
yeah,
top
yeah,
coming down like a
yeah,
chandelier. Now,
yeah,
all these microwave line are metal lines, semi-rigid lines, which are essentially carrying also microwave but also heat from the surface of the sun to the qubits. So this is exactly stupid thing to do. That you have a cooling system which you're pumping lot of energy to the kick it out, or on the other hand, you have connections which are bringing it heat. So beyond
yeah,
a point, increasing the number of wires doesn't help, because then the temperature will not be stable and you cannot do this forever and ever. So then why can't we replace? These are communication lines and
yeah,
control hardware. So why can't I have the control hardware inside the fridge at 4 Kelvin? And then we have some superconducting wires going in, which
yeah,
doesn't do the much of heat loading. And
yeah,
beyond that, that's a digital part, that you have a ribbon cable coming in, and with that you are able to control 1,000, 10,000, even a million qubit. That is
yeah.
possible. So this is
That,
one of the things I am also working in. So again, semiconductor comes to rescue.
yeah, yeah.
Yeah.
So now, if this is coming and increasingly it is getting to the again use of ease of accessing this, and increasingly you are bringing, IBM is bringing, and now there is definitely classical computer as a bit and qubit, right?
So sorry,
So
sorry.
yeah, are you able
Mhm.
to hear me? You are not able to hear.
Yeah, sorry, I actually missed the last part. I was no,
So
no.
what I,
That was,
yeah,
yeah, that was
okay now?
cut in between. Yeah,
Is it okay now?
it is. It is breaking in between. Yeah.
Is it breaking
Now,
all
please,
of?
please repeat. I would like to.
So my question is now, uh, the bit and qubit, right? They will work together for some time, right? So means we are probably going to the age of hybrid computing. I'm not talking about the hybrid cloud. I'm talking about hybrid computing where bit and qubit working together. We are well. So I would like to go to Dr. Suri. How this we are material science. We talk about semiconductor. We talk about bits, classical computing, and now the quantum is coming. How this hybrid computing world looks like from now to next 4 5 years of time.
Yeah, I think that's again a very interesting and also difficult to answer question, because a lot will depend on how like each of these fields evolve. But one thing is already that is being done in this context is like the interfaces. In this hybrid computing, the interfaces become very important. The interconnects between different type of computational platforms, they become very important. So well, let's talk even about like in the non-quantum space also. There is the advent of optical computing, or there are high-speed optical interconnects for high rate, extremely high bandwidth data management. So there we are already seeing hybrid technologies, lot of progress happening on hybrid hardware technologies, where optical electronics, optical interconnects are being manufactured for working with silicon based systems. So even to have the quantum thing integrated into the mainstream on the interconnecting or interfacing fabric, lot of such innovations have to happen. Uh, or the other way is that other natural way is that you have a data center of quantum computing which is powered completely by quantum computers, and whatever its input and output is, that is again digitized and treated like normal data stream for any other type of computational platform, any other standard computational platform. So either it will be in that kind of model where you have dedicated data centers of a particular type of computing fabric, or if you really want to physically co-integrate them, then this interconnecting technologies have to evolve.
Yeah, Dr. Amlan.
Yes, yes. Again, I agree with Professor Suri a lot in this. Yes, absolutely. This is what is going on. So I would say again buzzwords, right? Future belongs to bits, qubits, and neurons. This is the three triad they're talking about. So I would say, bits are already there. They're not going to go away anywhere. By the way, I want to have a disclaimer right now that all sorts of classical computing are going exponentially, and it is going to go exponentially high. It's not going to be replaced by any other kind of computing. Classic bits are going to stay and always be the bedrock. On top of that, neurons would be the next thing. It's already saying, we are seeing that neuromorphic computing and others different form of computing will come up. Exactly on top of that, probably something even higher speed with low power would be optical computing. And then comes the art of let's say the promise of quantum computing, which will be really jump and a different kind of computing. It is not that you will be able to play games or render things faster, or do data analysis faster, but yeah, somewhere some problems which you are not able to tackle in classical computing can be probably offloaded in quantum. So it is always going to be hybrid. So that is my answer. It is not going to be one thing or other. It is going to be the hybrid of in the regime of really lot of bits, a lot, then a bit lesser, but still neurons, and even lesser probably qubits. But this will be the stack.
And somebody like QPI, right, which is building data center technologies, right? So you are putting this vision together of getting this up
Exactly.
together.
Exactly,
Okay.
exactly. So even even before data center, it's already hybrid, in a
Mm.
sense that you have room temperature big chip, which is like an universal optimizer chip. What can be done classically should be done classically. Then it intelligently offloads and decides that this part is better have quantum correlations. This shifted. So even in the quantum computing part that we have a three chip solution. In the first chip itself is actually a room temperature classical optimizer. Second chip is again what I'm working on, 4 Kelvin, this control chip, which is like a motherboard to the quantum processor. And the processor can be of two types. Say you can have your superconducting or semiconducting. I preferably, from semiconducting background, I would say semiconducting, because scaling is given for me. So that is what would be the structure. So even with the one unit is also hybrid. And then you can think about that being replicated in a data center and having high speed communication through optical computing and optical transceivers. And this is what
Yeah.
one can envision.
So my last leg of question to both of you is like, so this is a future, right, in front of us, and and we certainly have the capability. We have you building this technology and playing important role to develop this technology. We have Professor Suri who is doing research in this area, right? And we talk about this decade is technology decade, and they should play important role in this area, right? So where we are in terms of playing a crucial role in this technology area, and what needs to be done academically, research wise, productization wise, and overall, uh, at the end of it, it has to fit into the capital market that we are into, right? Professor
Yeah.
Suri, yeah.
So I think academically, I would say we are fine. We are like any other country because R&D in the academic institutes is happening on all of these topics in more than one place in the country. It is happening in the top institutes. There are groups which are working on quantum computing, quantum communication. There are research groups which are working on neuromorphic computing, in-memory computing. So academically, yeah, perhaps the numbers can increase, the number of groups can increase. So academically, we are fine. Now the big missing part of the puzzle is having local capability to tinker around with to build hardware prototypes and to tinker around with that. Even many IITs or IISc has some state-of-the-art characterization facilities for characterizing materials, devices, and now also for high-end chips. But fabrication is where the main core ability to fabricate anything in semiconductors or mainstream CMOS or state-of-the-art CMOS. That is the main missing piece of the puzzle that needs to. That is the main capacity driver that needs to come. Even design-wise, we are very good. Design-wise, there is lot of design activity happening because that depends on CAD tools and normal computers, and that kind of facility is available everywhere, both government and as well as in institutions. So the core fabrication, the core clean rooms, that is where most of the effort should now come in to make any of this thing meaningful, either at the academic or the industrial levels. That is my thought on this.
Yeah, Dr. Amalan.
Yeah, I agree, and I want to add again, but again a bit of disagree on the point that yes, academics is doing very good, but looking at the size of India, we should compare not with a country but a continent. Essentially, now if I should say India, I should be like it's size of Europe, right? And you have a population much larger than that. So I have a very contrarian view in which people usually talk in India when innovation in terms of jugaad or kind of frugal innovation. Here I wanted to point there are some things where frugal innovation don't work. Semiconductor hardware is one of them. And if you want to go and really challenge, Europe, again, for example, quantum computing. I am very happy and really, really proud of the fact that the government has just announced 6,000 crores yesterday, and cabinet has approved it for the national quantum mission. That's a very, I celebrate this point. However, having said that, look at Germany. They are dedicating about last time I heard it was $2 billion, 2 billion euros into quantum computing. Being at, I understand they're a rich country, can do that. However, European Union already has 1 billion. In addition to that, Germany is committing 2 billion. So what I wanted to point out is that there should be a focused drive in academia and what I ask from government is that there should be a focused drive because academia in some sense are doing good. They are doing their best to publish new research. However, let's say I want to make a quantum computer out of superconducting qubits, or let's say I want to make a chip with some nanometer something. So this is not an innovation as such in terms of this thing. This is basically catching up. So the catching up must be done faster and with lot of money and will. I would even stress the will, with a deep focus for next 10 years. Then only you will be able to catch up. It is not going to happen soon. Even if people say I want to do it as soon as possible, it is this catch up if you want to do. And for quantum, we are already there, but we should not miss the bus. It is
Yeah, and then
ongoing.
keep it commercially available is very important, right? Then
Yes,
only
yes. Otherwise, there's no make no sense. Being in a private entity, I would say yes, commercial, and that's what I'm saying. You catch up, and then only you are able to do anything about it. If you say I invest $20 billion in a foundry, I should get back. Otherwise, that will be a problem. That's
Right.
the kind of, but there is world is open now, and I think there's a big opportunity, and India should think big. It should think like we are Europe rather than thinking like we are competing against one of the smaller countries in Europe, or relatively like that. So think big. That is what I wanted to say.
Yeah, and I think these are very important, and probably uh, we have startup means at least in quantum may not be core startups. Companies are like UPI and Quinu probably, but there are some startups which have been building solutions and
Uh,
coming in quantum.
Yeah.
Startups.
so,
Because-
now the audience also may ask some questions if there are any.
yeah. So, but I think we are coming to the uh, conclusion of the discussion, and I'm trying to look at the audience questions as well. But this is definitely very one of the great important conversation I have in the very important critical area of things that will shape up the future. And I really thank Dr. Amla and Dr. Suri to be part of this. So we'll probably conclude with a final concluding say from each of you, Dr. Suri first, and then Amlan, and we'll meet you in the future for some such kind of conversation in the future as well. And thanks for really adding value to the discussion we set up. So, Dr. Sri, to conclude your conclusion, then
Uh,
you have any
the
question? You have some question, Bhumika? Not really, right?
yes, yes.
What is the question?
Yeah. You have question?
No, not. So let's then conclude with Dr.
Yeah.
Suri and Dr.
Yes.
Amlan.
Ask.
I'm requesting Dr. Suri to conclude and then Dr. Amlan. So just concluding now.
Yeah. So thank you, Dr.
So I'm
Amlan and
asking
Dr.
Dr. Suri to Bhumika. Please wait. I'm asking Dr. Suri to give a concluding remark. But with that, we can close.
Okay. To conclude, I would say that all stakeholders, if we have to move ahead in this area, all stakeholders have to make some effort. Academia does some R&D, and the thing that is needed at academia side is to be fine tune their R&D more to real systems, real use cases. Government, obviously, it's always expected that more funds are given for the research, more resources are given. And where industry and user also need to play a very important part. The industry needs to take the initiative to reach out to local academia more. Industry needs to also push back in different ways to all the Western or whatever example tech societies or tech success cases we um, imagine. The industry has played a very important role of constantly engaging, patiently engaging with the academia. Industry cannot treat academia like a supplier. Industry has to treat academia like a partner. Which means it is an iterative process. Academia may not be able to yield to their. That is only how local technology ecosystem can progress. Whether we talk about these advanced technologies, so that kind of engagement, and even from the users, for the uh, when we are indigenizing or when we are developing technologies, we must the user has to be more sensitive for cutting edge or innovative technologies. User sensitivity also has to be there in an iterative nature. The and acceptability to an iterative nature. So of the solution that has come out, it cannot be if you are just buying the technology from somewhere, if you are getting it from somewhere, yes, you can expect a final clean cut product, but when you are raising it from scratch, then the expectations have to be more realistic, and even intermediate milestones have to be appreciated. So many times what we see that there is the call or request for some technology indigenization, and uh, the the requirements are listed, which are extremely as if the technology has been existing for the past 30 years. So if it is being indigenized for the first time, then the user or the customer expectation has to be more balanced. If we really, so it is an ecosystem thing, R&D, engineering, and all verticals of the ecosystem have to work in that iterative approach. Only then a base would come, and then from a catching up game, you will reach to a game where you are ahead of the competing teams.
Yeah, Dr. Amlan, with you we'll conclude.
Yeah, so I would like to again add a bit things. We are I would like to encourage now all the participants. I hope I believe they're all young. That is what I believe. Because India is a young country, and we are in the regime of the next decades would be Indian decade, being we are into the decade, is what is known as democratic dividend, where we have a large young population. And young population, in my opinion, loves technology. And the emerging tech is kind of in a synonymous kind of thing. When India emerges out of with this young population getting matured, so they would be the flag bearers, and they can take India. They should be open and think and embrace these new technologies that are coming up and make strides. And hopefully we will have when you have India, when you go to the next level where it is 5 trillion, 10 trillion, $15 trillion economy, I would see young this leaders in technology itself, in hardware, in semiconductor. That is the envision uh, that I would like to project on. Yeah, and that with that, thank you very much for having me on this platform.
Yeah, thank you, Dr. Amlan. Thank you, Dr. Suri, and really great to interact with you and learn from you both. Thank you for joining today.
Thank
Thank
you.
you.
Thank
Thank
you,
you.
Dr.
Thank you.
Rahman. Thank you,
Bye
Suri.
bye.
Thank you, Vinay, sir, for moderating the session.
Thank
Thank you.
आराम से बात किया करो